Hi all. We are up for a very fun section today, talking about factoring polynomials. This is stuff that sometimes you might be pretty good in it from your algebra-based classes, but no matter who you are, you can always really refine your factoring ability, and it's something that you're going to need to be able to do for future classes. Once you get into the calculus series, factoring becomes necessary, not only in the simplification of problems, but sometimes just in the setup. You have to be able to factor to get the problem set up in the very first step. And if you can't do the factoring, you're doomed to not be able to do the problem. So this is a pretty important section of information. Let me go ahead and pull up the PowerPoint here with you. So on this here, let's see. Oh, there we go. So when we look at factoring polynomials here, just talking about the objectives of what we'll be doing in this section, the first thing that you always look for when you factor anything is to factor out the greatest common factor. You should have already known that just from your previous factoring skills, is that the first thing you always do is try to factor out a greatest common factor between all of the monomial terms. Now, secondly, if it's a four-term polynomial, we'll factor by grouping. We have trinomial factorization by either the trial and error method or by the AC method. Both of those tend to work pretty well. Next, we'll factor using difference of two squares. That's probably one of the easiest things, but with the difference of two squares, you always need to make sure your answer is fully factored. Quite often, one of the factors needs to be factored further, and a lot of people miss that. Factoring perfect square trinomials, that becomes a pretty important technique, most notably in Calc 2, whenever we're integrating functions that end up being an inverse tangent. If you can't pick out the perfect square trinomial in the denominator, you can't work the problem. So those become of very importance later on. Factor the sum and difference of two cubes, and then use general strategy for factoring polynomials, just most notably using the greatest common factor first and then choosing something after that. And then we'll factor algebraic expressions containing fractional and negative exponents. That's probably my favorite type of factoring, and something students are usually not very good at coming into this class. So please, please, please make sure you focus on the homework questions that involve the fractional or even negative fractional exponents and how to factor those out. Okay, so first up, factoring polynomials. A factoring polynomial expressed as a sum of monomials means finding the equivalent expression that is a product. Now, a lot of times students, it just doesn't dawn on them, why would I need to get it written as a product? Because if you can get something written as a product set equal to 0, then you're able to solve for the variables, because we know by the zero product property, anytime you have terms multiplied that equal 0, at least one of the terms, if not all of the terms, must be 0. So that's an extremely important technique. Now, you'll keep on reducing all these factors down until there's no factors remaining in all of your terms, and that's when it's factored completely. Greatest common factor is what we always look for first. We'll always abbreviate that with a GCF. It's an expression of the highest degree that divides into each term of the polynomial. For example, here, if I'm looking at greatest common factor, I have 10x cubed minus 4x to the second. Well, okay, if I look at this problem, I can see between 10 and 4, they clearly both have a common factor of 2. And between x cubed and x squared, well, the highest power of x between the two is x to the second. Please keep in mind the greatest common factor of a variable term is always the lower power there. A lot of times people lose sight of that. It's always the lower power. Greatest common factor is the lower power of x in this case. So I take out the 2x squared. When I factor a 2x squared out of the first term, it's going to leave me with a 5x. And when I factor a 2x squared out of the second term, it's going to leave me with a 2. So you see now I have 2x squared times 5x minus 2x squared times 2. but that's because I factored it out of both terms. So you say, well, why not just call it 2x squared gets factored out. What's left over is the group 5x minus 2. And you would never, ever need to show this intermediate step. I would rather you just go from here directly to here, but I was just showing this intermediate step to show you that you could multiply back out to get what you had here. Now if I say, well, now I want you to factor, your first term is 2x times the group x minus 7. Your second is 3 times the group x minus 7. Well, clearly the common factor between this, your first term, and this, your second term, is the group x minus 7. So you'd factor out that group x minus 7, and now think about what's left over once you factor it out. If you factor the x minus 7 out of the first group, you'll have the 2x remaining. Factor it out of the second term, you'll have a plus 3 remaining. So our fully factored final form of the fantastic answer is x minus 7 times 2x plus 3. Now, that leads us straight into factoring by grouping. Factoring by grouping is the technique that you'll use anytime you see 4 terms in an expression, and it's when we cannot pull out a greatest common factor out of all 4 terms, but we can factor out in the first 2 terms and factor something out in the second 2 terms. Excuse me. So now, if I look at this problem with you, please note in the first step, you can't factor anything out of all 4 of those terms with the greatest common factor. However, if I ask you to group the first 2 terms together and then group the second 2 terms together. Now, using parentheses, if I'm grouping the second 2, I'm going to call that plus a negative 2x instead of minus 2x, because you create problems when you try to group after a minus sign if you don't change the sign of the term within. So instead of worrying about that, I just said, well, minus a 2x is the same thing as plus a negative 2x. Now I can group those out. In my homework solutions, you'll see that I handled this scenario by not using parentheses. Instead, I just underlined the first 2 and I underlined the second 2 terms to carry out the factoring by grouping. I kind of like that better than this, but for showing the work that's computed out, the parentheses work better. Now, in that first group, between x cubed and 5x squared, you can factor out an x squared. That's going to leave you with x plus 5. Now, instantly, as soon as I do that in the first group, I know that the second group better have an x plus 5 left over as well. If it doesn't, I've done something wrong. So here I'm looking at the second group, the negative 2x minus 10. First thing I need you to remember is anytime an expression starts with a negative, it's always best to factor that negative out. So I see a negative 2 and a negative 10. Well, I'll factor out a negative 2. I know that that's the right choice because it's going to give me the x for the first term when I factor it out. I'll factor out the negative 2. It's going to leave me an x, and negative 10 divided by negative 2 leaves me plus 5. So then I can say, all right, between this first term and this second term, I can see they have the common factor of the group x plus 5. When I factor that group of x plus 5 out, I'll be left with x squared minus 2. That's my fully factored final fantastic form of the answer. Now, what if we have, instead of a 4-term polynomial where we factor by grouping, we have a 3-term polynomial? So what we're going to do in that case is this strategy for factoring ax squared plus bx plus c. So assume for the moment that there's no greatest common factor. That's what you would always first do. If ax squared plus bx plus, if that had some greatest common factor, you would first factor that out. But now let's say you've either factored that out or there was no greatest common factor. After that, you're going to find the first 2 terms whose product, it will give you ax squared. So you say, I need to find 2 terms that's going to multiply together to give me the a term. So factors of a. And then you need to find the last 2 terms that are going to be products of c. So this term times this term has to give you the c. You can do trial and error between these 2 steps to find the terms that gives you the a and the c to work out the problem. So that technique absolutely fine. Let's go ahead and see that in action here. If I have x squared plus 13x plus 40, the first two terms have to be a product whose x squared. Well, there's no choice there. And please ignore that minus 80 and the plus there. I've copied down the polynomial wrong there, but that's irrelevant. Whether it's this polynomial or this polynomial, you already know the two terms that's going to multiply together to get you an x squared are x and x. So we would have the first two done. Now, we'll find the last two terms to be a product of 40. So they have to multiply together to get to 40. And so you just think, well, factors of 40 are 1, 40, 2, and 20, 4 and 10, and 5 and 8. That's the only factors of 40 that there are. So then you'd say, well, in the problem that we have, and again, ignore what I accidentally put in step 1, in order to get what we have, we need factors of 40 that sum to get to 13. There's only one option, the 5 and the 8. So now you're looking for the pair with the factors whose sums is 13. We get the 5 and the 8 is 13. So now we know x squared plus 13x plus 40 factors to be x plus 5 and x plus 8. If you get that, you're doing great. Now, difference of two squares format. We know that a squared minus b squared, or you should know, a squared minus b squared factors into the two conjugate expressions, a plus b times a minus b. We saw this in reverse in the last section where we multiplied a plus b times a minus b and got a squared minus b squared. Now we're going in the factoring direction to where we want it in simpler factors, a plus b and a minus b. So if I give you something like 36x to the second minus 25, you can say, okay, I know that 36x squared is the same thing as 6x times 6x, so I can write it as 6x quantity squared. And I know that 25 could be written as 5 times 5, so it's 5 squared. So I can say if I write this in the format of a squared minus b squared, it's written in the format of 6x quantity squared minus 5 squared. I know a squared minus b squared is a plus b times a minus b, so my solution set here is just going to be the factors 6x plus 5 times 6x minus 5. Now, if we have perfect square trinomials, so this is where your trinomial is in the format, the first term is a perfect square and the last term is a perfect square. If the middle term is twice the square root of the first term times the square root of the last term, then you have a perfect square trinomial in the format of a plus b quantity squared. If your first term's a perfect square and your last term's a perfect square, and the middle term is the negative of twice the square root of the first term and the square root of the last term, then it's going to be in the format of a minus b quantity squared. These problems are much better seen in examples so you can see what's going on. This one's be a pretty tough problem if I just gave it to you, but notice how we break this down. We can say, well, if I'm asked to factor 16x to the second minus 56x plus 49, the first thing I automatically recognize is that, okay, 16x squared, that's 4x times 4x. 49 is 7 times 7. So instantly I suspect, hey, this is going to be a perfect square trinomial. So that's what I'm saying. We suspect it's a perfect square trinomial because of that. Now, is it a perfect square trinomial? If it is, that middle term has to be twice this number times this number. So I can say, okay, 2 times 4x would be 8x, times 7 would be 56. Ooh, yes, 56x, that's what I have. Well, okay, I know that the middle term is minus. Please keep in mind, anytime the middle term is minus twice the square root of the first term and the square root of the last term, it's going to be in the format a minus b quantity squared. So I can say 16x squared minus 56x plus 49 is equal to 4x squared minus 2 times the square root of the first term times the square root of the last term plus 7 squared. I know that that's going to be factored as 4x minus 7 quantity squared. You always take the sign of b for what's in between the 4x and the 7 there. Now, had that been a plus, this would have been a 4x plus 7 quantity squared. Pretty nice problem there. Now, if you're factoring a sum or difference of cubes, these are formulas you really just need to commit to memory. If you have not committed these to memory, you should. Just like this difference of two squares, a squared minus b squared is a plus b times a minus b. You should never forget that. Well, you should never forget that sum of cubes is a plus b times a squared minus ab plus b squared. What I always remember is that both formulas have one minus sign in it. The difference of cubes formula has the minus sign in the binomial. The sum of cubes formula has the minus sign on the second term inside the trinomial. Other than that, the two formulas are identical. So I can say, okay, a cubed minus b cubed, a minus b times a squared plus ab plus b squared. The only difference in that and the sum of cubes formula is that I have a plus in my binomial and a minus on the second term inside the trinomial, and you got the two. Now, as far as using those, here I have a difference of cubes formula. What if I have 125x cubed minus 8? In order to apply the difference of cubes formula, you have to get this down to a number cubed minus a number cubed. So you can say, okay, no problem. The cube root of 125x cubed would be 5x. 5 times 5 times 5 is 125. And then the cube root of 8 is 2. So I can rewrite 125x to the third minus 8 as the group 5x cubed minus 2 cubed. Now I apply the difference of cubes formula. Okay, it's the first one minus the second one, 5x minus 2. Now it's the square of the first term, 5x quantity squared, and then plus these two multiplied by each other, 5x times 2, plus the second term squared. Then it's just an act of simplifying. The binomial expression is done, but the trinomial, I'll need to say 5x squared is 25x to the second, plus 2 times 5x is 10x, plus 2 squared is 4. Fully factored final form of the answer. Please remember, you never have to worry about thinking whether that trinomial is factorable. In this case, you might think, well, hey, is that a perfect square trinomial? Nope, nope, nope. It never, ever is. The trinomial you get from the difference or sum of cubes formula is always prime. So there's no need to think whether it should further factor. It will not. Now, a strategy for factoring polynomials, like I was saying at the very beginning of this lesson, the first thing you always do is to try to take out a greatest common factor. And sometimes you'll do that in combination with other factoring steps after that. After you've tried that, whether or not the greatest common factor could be factored out, you'll go on to step 2, and that's to determine the number of terms in the polynomial and factor as follows. If there's 2 terms, the binomial could be factored by either difference of 2 squares, sum of cubes, or difference of cubes. Please notice there is no factorization for sum of squares. So if you have an a squared plus b squared, it's prime. Now, if there's not 2 terms, we move on to the 3-term case. In the 3-term case, what you'll be looking for is either a perfect square trinomial or trinomial factorization. So that's where you're going to have to try to find factors of a times c that sum to get to b. And you'll see that I've used that AC method in the homework problems quite often. So please make sure you refer to any homework for questions on how to do that. I didn't do a whole lot of that here in the videos because I would expect most of you are very comfortable with the AC method from previous algebra classes. If there are 4 or more terms, try factoring by grouping, which we did at the beginning of this. Check to see if factors with more than 1 term can be factored further. If so, we must always factor completely. That's a common thing that I see students miss on tests is they will factor wonderfully in the first step, but then once they get to something that looks like it's factored, they just want to stop rather than thinking, is each factor fully factored or could it be factored further? And if it can be factored further, It should be factored further. Okay, some examples of that. If I have 3x cubed minus 30x squared plus 75x. First step, look for that greatest common factor. So you'd say, well, clearly I could factor a 3 out of all three of those terms. I could also factor out an x. Okay, so if I factor a 3x out of all three terms, the first term is going to have an x squared left over. The second term would have a 10x, and the third term would have a 25 left over. Now you say, okay, I factored out the 3x. What about what's left over? Could it be further factorable? And this step, you should look at it and say, ooh, the first term and the last term are both perfect squares, x times x and 5 times 5. Is that middle term 2 times x times 5? Yeah, it's a 2 times x times 5. It's a 10x. Gorgeous. We automatically know that's the case where we have our perfect square trinomial. I was getting too excited. I almost forgot what to call it. So now with that perfect square trinomial, you can just say, since that middle term is minus, that's going to be x minus 5 quantity squared. So you'll see that's what I was telling you down here in step 2 is to recognize the perfect square trinomial, factor it to show that x squared minus 2 times x times 5 plus 5 squared. And you say, well, that's in the perfect format of the perfect square trinomial where I can just call this x minus 5 quantity squared. Now, could have you also factored that and said, I'm looking for factors of positive 25 that are summing to negative 10 and get, well, negative 5 times negative 5 is a positive 25. Negative 5 plus negative 5 is negative 10. So it factors to be x minus 5 and x minus 5. That's fine. But the format of the answer I have is superior to that, where you write it as x minus 5 quantity squared. Though I wouldn't count it wrong if you wrote your x minus 5s out twice. So none of the factors can be factored further. So we're done with that problem. Now, this is where I really want you to focus on. It's the homework questions at the very end of this section. I want to make sure you can factor with fractional and negative exponents. So although expressions containing fractional and negative exponents, they're not polynomials, they can still be simplified using our factoring techniques. And we really need to be able to simplify them for aid in future classes as well. For example, so if I give you this expression here, the first thing I would like to ask you is how many terms does this expression have? You have x times the group x minus 1 to the negative 1/2 plus the group x minus 1 to the 1/2. What I want you to understand is that anytime you see terms being multiplied, I think of this as all my first term. It's x times the group x minus 1 to the negative 1/2. That's all my first term. Your second term is this group right here, x minus 1 to the 1/2. So then it becomes a matter of saying, well, what does this term and this term have in common? And it's obvious. They both have in common the group x minus 1. But here's where I frustratingly see students make a mistake. When I say, what's the greatest common factor? So many students will say, well, hey, maybe I can factor out an x minus 1 to the 1/2. Might as well. No, that's horrible. And the reason it's horrible is whenever you factor something out, a greatest common factor out, you should always remember you're factoring out the lower power. Just like if I say, hey, take the greatest common factor out of x squared plus x cubed. You'd factor out the x squared and say it's 1 plus x left over. You always factor out the lower one. So I can say, well, okay, between x minus 1 to the negative 1/2 and x minus 1 to the 1/2, the lower power is that negative 1/2 power. That's why I'm saying the greatest common factor in this expression is x minus 1 to the negative 1/2. Now, I've really shown the steps in factoring this out, and please don't think you would have to show this many steps. I'm just trying to make sure you understand the process here. So this is the problem I originally gave you to factor. And then the first term already had the expression x minus 1 to the negative 1/2 that I was going to factor out along with that x. Now the second expression, I want to factor out an x minus 1 to the negative 1/2. Well, it was x minus 1 to the positive 1/2. Notice if I multiply that by x minus 1 to the first, then you say, well, x minus 1 to the negative 1/2 times x minus 1 to the first, I would have to multiply like bases. I would add their exponents. This just will give you back the group x minus 1 to the positive 1/2, because negative 1/2 plus 1 would be positive 1/2. Okay, the point I'm trying to make now is when I factor out that group x minus 1 to the negative 1/2 out of the first term, and personally, I would never show this step of work right here. I think it's unnecessary, but I put it there just to help you see what's going on. So I factor it out of the first group, I get an x left over. I factor it out of the second group, and what you should always do is say, well, if you factor out, you divide. When you divide, you subtract exponents. So I'm going to have an x minus 1 to the 1/2 minus a negative 1/2 power. That's 1/2 plus 1/2. You're going to have an x minus 1 to the first power left in there. Now, the nice thing about having the x minus 1 to the first power left in there is you really don't even need a group around that anymore. X minus 1 to the first is just x minus 1, which means we can combine our terms of x and call it 2x minus 1 inside that group. And now, for my final step in simplifying, it's considered improper notation to have a negative exponent in your final answer. So I'm going to say, well, that group x minus 1 to the negative 1/2 can be pushed down to the denominator, and my final fully factored final fantastic form of the answer would be 2x minus 1 over the group, and I do need a group on that, x minus 1 to the positive 1/2 power. It's a glorious problem. Now, if you followed me on that, wonderful, but whether you did or not, please make sure you really focus on the homework problems towards the end of the section. They'll all get into stuff like this. I've shown my work and my homework solutions as much as possible, but I would love to work with you if you have any trouble with those. I need to make sure you're confident with those problems. Okay, guys, that finishes up this section. Please do try the homework solutions and let me know if you have any trouble. I'll be glad to help.